So what I wanted to do while I'm working on getting some of the more formal lecture materials together for you guys was to go through a few example problems of how to use some of the equations in this chapter. Okay, this is one of the more heady chapters in the entire semester. And so I wanted to do some explicit problem solving here. All right. Now these are not your homework problems, but these are problems that have some similar flavor to some of your homework problems. Okay. And specifically, I want to look at problems 44, 56, and then a problem out of another book. But one of my favorite problems, just because of the thinking you have to do to set it up. All right. But let's work through these one at a time. So the first problem, 44 out of your book, asks if we have a superconducting wire of diameter 0.25 centimeters and it carries a current of 1,000 amps, what is the magnetic field just outside the wire? So when we have questions like this, what we're really asking is, what is the magnetic field right at the boundary between the wire and beyond the wire? Okay, and so what we effectively do is consider the wire, consider the magnetic field at the edge of the wire. Okay, so if I have a wire that is, say, maybe going into the screen there, and it has a radius of 0.125 centimeters, or a diameter of 0.25 centimeters, and it's carrying a current of 1,000 amps, what is the magnetic field? Okay, now the magnetic field is going to be evaluated right along the edge of the wire here. So if the current is, say, flowing into the wire, right, if the current is flowing into the wire, then the magnetic field is going to be looping around the wire that way, right? And it will get smaller and weaker the further out you go. Okay, but it's looping around the wire this way. In any case, so what we do is we use Amperes Law. Okay, in this case we use Amperes Law, which says the dot product between the magnetic field and a line element along an imaginary loop. Okay, so the DL acts an awful lot like the DA does in Gauss's law. We draw an imaginary loop around the current, and whatever fraction of the current that loop encompasses, okay, is going to dictate the strength of the magnetic field. Now in this case, if we draw our Amperian loop directly around the edge of the wire, then we're going to be encompassing the entire current. And so what we do is the circumference of our Amperian loop that goes right along the edge of the wire here is going to be just 2 pi r, where r is the radius of the wire, and that's going to equal the magnetic constant, or the constant of permeability of free space, okay, multiplied by the current. And the permeability of free space has the value 4 pi times 10 to the negative 7, and the units on mu naught are Teslas times meters per amps. Okay, and so basically this mirrors Gauss's law an awful lot, right? Because when I have a good symmetry, and my DL turns into just a regular shape, like the circumference of a circle, then the magnetic field is going to be constant on that circle, and it can be pulled out of the integral, and the integral of DL just goes to the circumference, right? So that's how we go from that step to that step, all right? And then it's just plug and chug, right? We're just solving for B, so we divide both sides by 2 pi r. 4 pi can be divided by 2 pi, which goes to 2, so I'm left with 2 times 10 to the negative 7 times 1,000, and then I divide by the radius of the wire, and my final answer just along the edge of the wire is 0.16 Tesla. Okay, 0.16 Tesla. And as I move further away from the wire, that will decrease. Okay, problem 56 involves that of a toroid. Okay, I can't really draw a toroid with this software, so I'm not going to bother, but you can see the examples of what toroids look like in your book. They're kind of like the wire that's wound into a donut shape, kind of, right? And the problem says a toroid has 250 turns of wire and carries a current of 20 amps. If the inner radius is 8 and the outer radius is 9 centimeters, what are the values of the magnetic field inside the toroid at distances of 8.1, 8.5, and 8.9 centimeters? Okay. Now your book gives the formula for the magnetic field of a toroid. It derives it for you, so I won't replicate the derivation here. But the main result is this: mu naught times n, which this is the number of turns. So in this case, we have 250. So this is 250. That is the number of turns. I is the current. And then 2 pi r is the circumference of a circle inside the toroid. So your toroid has two boundary radii, the inner radius and the outer radius, right? I suppose I might be able to draw that. So your toroid should look something like this, right? And then wire wrapped around it like this. Maybe I can draw a toroid. Not very well, but I can draw a toroid. So this would be the inner radius, and then that would be the outer radius. Okay, so this is 8 centimeters, that's 9 centimeters. And so the field is going to be evaluated at different points inside the wire, right? Toward one edge, the inner edge right here, toward the middle right here, and toward the outer edge right, didn't mean to do that, right here, right? So literally this problem is just plug and chug, okay? But it's knowing that this is the formula to do it, right? So most of your problems here are simply going to be dependent on you knowing what values to use, okay? So we can plug our values in and we can calculate the results. Now, the first and second numbers, okay, are not going to be identical, even though they're identical here, because here, by the way, I've already taken out the 2 pi and divided out the 4 pi here, so I'm just left with 2 times 10 to the negative 7. But in any case, right, so in one case I'm taking this top number, which doesn't change in any of the calculations, and dividing it by a different denominator. However, the difference between these two results is so minuscule that when the number is rounded to 3 decimal points, the answer turns out to be the same. Okay, so when you round due to sig figs, the answer turns out to be the same. When you do the same calculation with the outermost value given, then the value does drop. Now, a couple of things to note here, okay? So in a reasonably small toroid, so this is a donut of about 9 centimeters on the outer edge in radius, okay, and 8 centimeters on the inner radius, and you can see that really close to the inner boundary, the magnetic field is 0.012 Tesla. Near the outer boundary, the magnetic field is 0.011 Tesla. So the magnetic field for a reasonably sized toroid does not change very appreciably within the internal toroid itself. And so that's a fairly important result, that the magnetic field is not completely constant, but it is close inside the toroid, okay? Again, it's not completely constant, but it is close. Okay, on to a very challenging problem, okay? But this is a very interesting problem, so I encourage you to watch this video a couple of times and work through the derivation yourself. And so the problem is we have a sphere of radius r, and it has a uniform volume charge density throughout, and it's rotating. So I have charge, and it's rotating, and I want to determine the magnetic field at the center of the sphere when it is rotating, and that rotation is constant. So it's rotating about the center axis with an angular speed omega, right? Now, since this is charged and the volume charge density is constant throughout, these charges are basically spinning in a circle, and charges that are in motion constitute a current. So, even though this is a solid sphere, what I can do is I can kind of hollow out a ring of charge, right? So imagine that I've hollowed out a ring of charge, and I set, ooh, that's terrible, and I set that ring of charge into motion, right? So I've hollowed out a ring of charge, and I spin that ring of charge around this way, around an axis here, okay? Then since this is charged, the moving charges will constitute a current, and I will get a magnetic field that looks like this, right? I'll get a magnetic field that looks something like this. And so the sphere will ultimately be magnetized. Now, what I can do is once I have this current and this magnetic field, I can integrate this ring to go from the center of the axis out to the edge to get a complete disk. And that disk will then just have a radius r, okay? Then I can integrate over the entire sphere, which can be thought of as a stack of disks, okay? It can be thought of as a stack of disks. So that's the strategy, okay? Get the current of a ring, and from that current, get the magnetic field, okay? So, now remember that the definition of current is Q over T, right? The definition of current is dq over dt, right? So what I need to do is I need to find a differential charge element, and I need to find a time, okay? So to find the differential charge element, just go back to the definition of charge and charge density and say, okay, dq, my differential charge element, is equal to the charge density times the volume element that it encompasses. And for a ring, the volume element that it encompasses is going to be 2 pi r times dr, right? That gives me the surface area of the ring, 2 pi r dr, and then the thickness of the ring dx gives me my third dimension. So dq is going to be equal to the charge density times 2 pi r dr dx. Now, we're told that this has a constant angular speed, and when things rotate at constant angular speeds, they have a regular period. So it takes one full cycle for the period to be complete. And the period and the angular frequency are related by the formula 2 pi over omega. Okay, period is equal to 2 pi over omega. So what I can do is say, okay, this is a differential current element compared to the entire current in the sphere, okay? So this differential current element is going to be equal to the charge that's on that element divided by the total time it takes to complete one circle. And so I can take my dq, rho 2 pi r dr, divide that by 2 pi over omega, and my final result is this, okay? So then what I do is go through and find the equation for a charged ring in the book. And this is your magnetic field of a charged ring. Insert that charged ring expression into the expression for the magnetic field, and then integrate across the sphere from 0 to the full radius of the sphere, and then from negative r to r in the x direction to encompass the entire direction.